Uh-huh. Okay, and everybody can see my screen okay?
Yes.
Okay, perfect. Okay, yeah, thanks, Marshall. I appreciate it. Yeah, so my name, again, is Luke Sheneman. I'm the Director of Research Computing and Data Services here at the University of Idaho. My team supports research computing infrastructure, but we also do a lot of database and web application development and things like that, and super happy to be a part of this EPSCoR Track 2 project that is called TICBase. And I'll talk quite a bit about that. So what is TICBase? So TICBase is, it's a project where we're building a data repository, and it's got a couple of different objectives with this data repository. So it's about ticks and tick-borne illness. And the idea is that this is a data repository that's intended to be a centralized global resource for discovery and access, specifically to tick and tick-borne illness. So it's intended to be this destination repository that people who are in this area or are interested in learning more about ticks and tick-borne illness, it is a go-to resource for them. It's also intended to be used for publishing data within our project, and then using the data that we collect in the repository to be the basis of some more advanced things, like being able to develop semantic knowledge graphs and to be able to power some sort of data interoperability with other data platforms. And all of this is in service to the idea of fair data. And I suspect most of you know that, which is to say that data is findable, accessible, interoperable, and reusable. So this was a cross-institutional collaboration. So we worked quite a bit with University of Nevada, Reno on this. They took a little bit of a different tack than we did at University of Idaho. So they focused on the collection of research articles, so peer-reviewed journal articles and that sort of thing. Whereas here at the University of Idaho, we were interested in cataloging more the data sets that are available that describe or have to do with ticks and tick-borne illness. And so collectively, we were able to come together and create a resource that kind of brings both of those things together. The University of Nevada, Reno created a thing called Tick Crawler, which was really intended to go and scrape all of the resources at PubMed, but then also Semantic Scholar and some other common large catalogs, and put that all into an Elasticsearch search index with an API, and then from that be able to do things like build knowledge graphs, entity networks, and do some general text mining. On our end, like I said, at the University of Idaho, we focused on getting data sets or metadata for data sets from data repositories, and we created our own system for doing that. We had a student that worked with us for a summer that worked with a variety of data repositories and developed a relatively simple architecture, this kind of hub and spoke architecture, where he created a tick-based data crawler that would connect to the API endpoints of these various repositories based on a curated set of search terms that we worked with Nevada to develop. We basically identified resources within these data repositories, harvested them by connecting to their particular API endpoints in the way that they require, and then develop a method for ingesting that then into a DSpace-based data repository. And if you're not familiar with a DSpace is a really common metadata catalog used by libraries and others. It has a search engine, it's very extensible, and it has a very powerful API. And so this was the original development. And so by sort of middle of last year, we had tens of thousands of articles and metadata records that were ingested into this DSpace catalog. It included articles and data sets, and we considered it somewhat fair in the sense that the resources within this were findable, accessible. We had links back to the original articles, things like that, or the original data sets. And we also had a very powerful API that we could then use to do sort of next level things like semantic and spatial search and things like that. So that was where we were last year. But then we got a lot of questions from researchers like, this is all great and stuff, but what you've really done what are you doing that's different than, say, Google Scholar or just using the PubMed search interface? What is different other than just concentrating it all into one place? And that was really our answer, is that we were concentrating all of these resources into one catalog, specifically focused on ticks and tick-borne illness. And because of that, it added value. But we really started thinking, like, what could we do to really extract additional value? What's the value proposition of tick-based beyond what's already available with PubMed and Google Scholar? And of course, in that interim time, the world has sort of changed, right? So now we have, these very powerful large language models that are now available, whether it's Google Gemini or OpenAI's GPT-4, Claude Anthropic, and those types of things, right? So the landscape has fundamentally changed in the middle of our tick-based project. And so it got us thinking, like, okay, well, what can we do to take advantage of this revolution in large language models that, and all of the ecosystem of tools and resources that come with that? How can we apply that to tick-based? And it was really my coworker, John Brunsfeld, who's on the call here, who really got into this world and really identified where we could add value by applying these large language models to this kind of thing. So can we harness the recent explosive advancements in AI to add compelling value to the tick-based experience? And specifically, can we curate our tick-based collection using AI? Can we really make our collection of resources very focused and high quality, make sure that it only captures highly relevant resources that are related to ticks and tick-borne illness? We don't have a lot of false positives. Can we use AI to help navigate that sort of curation? Can we use AI to summarize our articles and data sets and present it to the users in a more friendly user interface? And can we enable true semantic search? And I'll talk a little bit more about how we define that and how we use that. And can we use AI to perform geolocation? So a lot of these articles and data sets have some sort of spatial component to them, right? Whether or not, whether it's an article that's describing an experiment or a field study at a specific location, or what, it would be great to be able to pull that out of the natural language and be able to use that as a part of the search criteria and help build our knowledge graphs. And can we use AI to meaningfully find similar resources? So semantic search, brings together a number of different things, right? It's sort of like the broader context of your query stream and whoever the user is, the ability to recognize entities and use natural language to sort of understand the meaning behind things. So you might be looking for something in particular, and when you do that with a semantic search, you might actually be able to identify related things and then build out sort of a semantic knowledge graph of either similar resources or similar concepts. And so that's where we saw the power of enabling semantic search. And really it's about, finding what you mean to find, not just what matches your exact keywords, right? And so this is an example that I really like to use to demonstrate this, right? So you have this question, right? Or this query prompt that says, give me a zesty, tangy chicken dish recipe with little green leaves that make your tongue dance, right? So in the traditional lexical search, it might try to do some sort of exact word match across some sort of index or catalog, where you're trying to match words like zesty, tangy, tongue dance, and things like that. And you might end up getting things you didn't really want, right? I think it's kind of funny, but do not Google tongue dance. You're going to find some resources that you don't necessarily want to see, right? So doing an exact lexical search might not get you exactly what you want. You might hit matches that are false positives or that are off track, that don't take the entire context of what it is you're asking for. Whereas a semantic search understands sort of what you mean a little bit better. It understands, okay, little green leaves may mean cilantro, and zesty, tangy, well, that may very well be something like lemon or lime. And so it really can hone in on what you really meant to find using semantic search. So if we can apply this now to scientific literature and scientific data sets, and actually power a search where you actually can find what you mean, then that'd be much more powerful. Okay, so right now, with the current situation with large language models, the way that they handle vector embeddings, and I'll talk a little bit more about that, allows you to do similarity search. So you can do semantic similarity search across different concepts or different documents to be able to find, to be able to power your semantic search. In the, the sort of alternative way, or the way that's been around a little bit longer, is to be able to define sort of knowledge graphs explicitly, trying to understand entity relationships between concepts or resources using something like RFD or some other sort of method. But with large language models and the ability to create semantic embeddings, we're now able to do similarity search very easily and very automatically, which is pretty powerful. And the way we do that, right, is to use vector embeddings. And so what you do is you use an AI model called an embedding model, where you can take an object, and that object may be a sentence, it could be a word, it could be a document, it could be an image, whatever. You pass that through the appropriate embedding model, and what you get for that object that you pass through is a vector. And the vector is just a list of numbers, right? And usually it's very highly dimensional, right? So you're usually talking about hundreds, if not thousands, of floating point values, all in a one-dimensional array. And that vector representation captures the semantic meaning of the object, right? So it takes the broader context based on how that embedding model was trained in order to produce that embedding vector. And the embedding vectors are really, you really think of them as vectors in the sense of physics, where you have a magnitude and a direction, right? And different concepts can be captured as sort of these arrows, right, through this highly multidimensional space. So on the right-hand side here, you can see, there's puppy and dog are actually relatively similar concepts. And so their semantic direction in this multidimensional space is really similar. The angle between them is relatively small, whereas a house, for example, is much further away from the concepts of puppy and dog and that sort of thing. You can use different methods for rapidly comparing two embedding vectors. The method that is most commonly used is cosine similarity, and the reason that we use cosine similarity is because it measures the angle between the vectors, but it normalizes it for the magnitude. So the magnitude is thrown away, so it's really useful for comparing text chunks of different lengths, because that magnitude is not considered. So cosine similarity is a great way to find the angle between two semantic vectors, and that's what we used. To implement our semantic search, we used vector database, and there's a number of them out there. Some of them are commercial, like Pinecone, Elasticsearch. There's a commercial version of that. ChromaDB is what we ended up using. It's open source, freely available, and relatively straightforward to use in Python. And the idea there is that you can take text and pass them through an embedding model and create a vector database that's populated with the semantic vectors, and then be able to do semantic search and other operations on that vector database. Okay, so that describes kind of the vector database part. There's another part here, which is to use large language models, for various functions in our semantic tick base. And there's a number of them to choose from, and I'll go into exactly how we use them. But we ended up using Mixtral 8x7b, which is an open source, open weights model that we can run locally. And so we created a little tick-based large language model inference architecture here with a couple of servers and 4 GPUs, where we were able to take our entire catalog of resources, or whether they're articles or whether they're metadata records for a data set, and we were able to do summarization and classification of those resources, and I'll talk a little bit more about that here in a second. But we were able to use our local infrastructure to do this over the course of a couple of weeks, just sort of iteratively running this, over a 4-bit quantized version of Mixtral. I'm going to go ahead and skip this slide in the interest of time, but so the idea here is that we use AI in the way, using Mixtral here to curate resources from our collection, from PubMed and Semantic Scholar and data repositories, into a collection of highly relevant tick articles. So this is how we use AI to curate our resources. So we grabbed all of PubMed and all of Semantic Scholar into almost 200 million resources. Using just keyword filtering, we were able to filter that down into a list of 400,000 resources. But we found when we looked at it carefully that there was still a lot of false positives. When you're creating a catalog of resources having to do with ticks and tick-borne illness, there's a lot of times where those keywords can be misunderstood. So tick, for example, can mean different things. Not all of them have to do with the parasitic arthropod, right? And so we then took the 400K, which still had a lot of false positives, and ran them through large language models to try to do a classification to make sure that we understood whether or not those resources were truly related to ticks and tick-borne illness based on what the large language models were able to decipher. And so from that, we were able to distill that original 193 million articles that were all of PubMed and Semantic Scholar down into this really highly valuable, pretty accurate collection of 81,000 records that are very specific to ticks and tick-borne illness. And so we used Mixtral in the way, that I described earlier to do the following in one pass, right? So we did this classification. So basically, look at the article and identify whether or not the article is about ticks or tick-borne illness. And then if so, let's summarize the abstract. So take the abstract from the actual resource, summarize it in a really concise summary using a large language model into 2 or 3 sentences. And then we also do language detection, right? So we also say, okay, is this in English or Russian or French or whatever? We do that sort of classification. And we do that all in one path using a prompt for a large language model, again, using our Mixtral API. Then what we do is we take once we have our sort of LLM sort of vetted, highly curated set of resources, then use calculate our embeddings for example, the abstracts. In fact, our summarized abstracts to calculate the embeddings for those, and then store those in our vector database. And so what we ended up doing was using sort of the default embedding model that comes with ChromaDB, which is this all mini LM L6 v2, which will take a chunk of text and convert it into a 384 dimension vector, right? And so for each one of those vectors, for each one of those chunks, we have, for example, for a distilled abstract, we computed the semantic vector for that and associated it back to the sort of the original abstract. And so now we have this vector database, and we point it not just to the original abstract, but to the entire metadata record for the resource. And so now we have a way of doing search against our vector database, doing semantic search, and to find resources within our catalog. Where we had the full text of the articles, and in our case, we had about 10,000 out of the 80,000 or so, where we actually had the full text of the articles, we actually broke that up using a large language model. We had it parse those out into sort of the main sections like abstract, introduction, description, methods, results, conclusion. We did that all with our Mixtral AI, and then ran each of those separate things. We summarized them and then ran those through an embedding model to create semantic embeddings, not just for the abstract, but for each section of the documents, right? So now that allows you to do some really powerful sort of semantic search, not just of the high level sort of thrust of the paper, but of individual sections, like, for example, your methods results section. And so we did the same thing with data sets, right? So with Mendeley data, Figshare, data dryad, be able to take our metadata records, do the extraction summarization, and create the semantic embeddings. And then wherever possible, we added in links between data and articles. So if an article referred to a particular DOI for a data resource, we wanted to make sure that that was captured in our metadata record. So in our user interface, you could go from article to data, data to article, and vice versa. Okay, so the user interface allows, this is kind of a screenshot, the top is kind of a screenshot of our user interface. And you can see, I provided a search term up here that says, okay, give me examples of Ixodes scapularis, which is a tick species, that are causing human health impacts in rural New England. So that was my semantic query. And you'll get a list of results based on that semantic search against your vector database. You can also do text search or lexical search. So basically it backs out back to a keyword kind of search. And we also have the ability to do locations and data sets in particular, and I'll talk about that in a little bit more detail. But we did allow for users to interact with the repository, either semantically or lexically as needed. And they do get different results. So this was what you're seeing here are the top results for these two different situations. We also decided that it was important to do geolocations of articles and data. So, like I mentioned, a lot of these resources have some sort of spatial aspect. Maybe the ticks were collected in a particular area, or there's a study site, or maybe you're talking about a very specific point in space, like a lat long, or possibly a named location or an area. So what we wanted to be able to do was to be able to take the title and abstract and other aspects of the document, and then do named entity recognition. And so we did that with Mordecai. So Mordecai, the current version of Mordecai, which is a library in Python for doing geoparsing, uses Spatie and transformers in particular to do named entity extraction. So identify all of the named entities or of locations within an article. And then we used geonames, which is a gazetteer for basically just doing a lookup of named entities to specific spatial locations, and then store that in our Elasticsearch index. So we're using Mordecai as sort of the AI framework for identifying named locations, and then just using geonames as a sort of a lookup. But to do this effectively, you really have to look at sort of the broader context. When you're looking at a named location, it's important to look at not just the name itself, but the accompanying context within the document. Because, for example, there may be a number of places called the Snake River, for example. There's one here in Idaho called the Snake River, but there's other snake rivers in the world. Which one do you mean? It depends on your context. And so using something like a natural language transformer allows you to look at that sort of broader context around the named entity to really pinpoint exactly which one you're talking about, and then look it up in geonames and then store it correctly. So that allows you now to do, semantic, lexical, or location searches in our portal. And so, the power of finding similar meanings to, the semantic sort of search is really powerful, right? So this is again a screenshot of the user interface of TickBase. In this particular case, I did a semantic search just for Ixodes pacificus, which is another tick species. And I was able to get an article that matched that semantically. And what we do is we return some number of results based on their distance, semantic distance, their cosine similarity from the vector embedding of the search term that you specified. And so we're able to get a graph that shows sort of related concepts, publications, and data sets that are related to the semantic search that you did. And then be able to show similar concepts. So on the left here, you see there's similar concepts are shown in the table to the left. We can, for the articles that have the full text, and we break out the different sections like methods, introduction, conclusions, discussion, we can actually find similar, do a similarity search for just those parts of the article or metadata record. And so we can, for example, be able to find similar methods potentially across different disciplines and domains, by using semantic search, where you've computed the semantic vector embeddings for their method sections, and then across lots of articles, and then be able to, identify the use of similar methods, even if you're not exactly matching, domain-specific jargon so for example, a lexical keyword search. So that's really powerful, and I think there's a lot of promise to being able to, identify research papers and research outputs that utilize similar methods or have reached similar conclusions, or intersect in some way that's beyond just sort of exact jargon matching. So I wanted to point out, I mentioned just briefly that we used a local AI model. We used this Mixtral AI model, this 8x7B model. And so this was open source. It required some fairly large GPUs. So we ended up, we went out and bought a couple of servers and 4 GPUs that were all used off of eBay for this particular sort of proof of concept project. We put this together. The whole cost of that, was about $10K just in hardware. Once the expense was spent on that, then the use of it was free from then on. And we got really good success using Mixtral to do the summarization and the classification of all of the resources in our catalog. We processed about 500,000 scientific articles and data sets over the course of several weeks. And we calculated that had we used sort of an, like an OpenAI API, it probably would have cost the same amount of compute would have cost probably 20 or 30K. And so just a shout out to the open source models that are available for doing this kind of, compute intensive work to create that summarization and classification. So there's lots more things that we're doing, and I know John is in the middle of exploring some of those things right now. But one of the things we want to do is add more articles and data set providers to our catalog, right? So we're basing most of the catalog is based off of the original work, text crawler work that our colleagues at University of Nevada, Reno did. And that was a couple of years ago. So what we want to do is make sure that we added additional journals, publishers, and repositories to the list. And we would like to make sure that we can automate the harvesting and ingestion of that, or at least provide some sort of guidance on how to do that. Increase the number of indexed full text articles. Like I said, out of the 81,000 or so, we might have 10,000 articles that are full text. We need more, I think, to really power the ability to do semantic search for document sections. We have a manuscript that's currently in development. Tanner Barrelman from my team is kind of leading the writing of that, and it's coming along pretty nicely. Hopefully, it'll be a good output of this project. And so just a shout out to, again, John Brunsfeld, who's the main developer of this tick-based tool, and Tanner Barrelman, who was instrumental, especially in the geolocation and named entity recognition portion, and is currently leading the writing of the paper. If you go to tickbase.net, you can find a link on that website to our data repository, and feel free to look around. It's live. We've got a lot of things in the works right now. So what you're seeing is a version from a couple months ago, but we've got some new things that John and others are working on. So with that, I'm happy to answer any questions you might have.
Yep. Thanks a lot, Luke, for this wonderful talk. We do have time for comments and questions. Do you have any from the audience?
Oh, Well, I think I have a quick question.
Yeah,
Hi,
go ahead.
Lucas.
Yeah.
Appreciate your presentation. And I hear that you mentioned you applied the Mistral with a parameter size of 7 billion and running it on your powerful hardware groups. And I'm wondering, have you ever tried other open source large language models which with even larger sizes? And how about the Llama 3? Thanks.
Yeah, so at the time we were looking at Llama 2 and Mixtral. At the time, Mixtral 8x7b, which is a sparse mixture of experts model, that actually has, it's actually closer to, I think, 48 billion parameters, but because of the sparse mixture of experts architecture, it only uses about 14 billion during inference, so it's relatively fast. But because of its size, as far as model parameter size and its architecture, it actually outperformed Llama 2 on most benchmarks at the time that we deployed it. So that's why we went with that. If I were to do it again today, I would probably look at using Llama 3, but that's only recently come out. Yeah, so I think we had to use we wanted to make sure that we had as many large language models available for these queries as possible. So we basically had one running on each of the 4 GPUs, separately, and so we had to use 4-bit quantization for our Mixtral model, which meant we were using about maybe 38 gigs out of the 48 gigs of video RAM on each GPU. We could use a larger model, but it would require spreading that across multiple GPUs, and then things would have gone a little more slowly. But we found really good results using that 4-bit quantization. But yeah, if I were to do it again, I think I would look at using Llama 3.
Thank you.
Yeah, I see Ethan pasted a question in the chat box. Do you want to just talk about it, Ethan, or I can read it for you?
Oh,
Yeah,
hi, yeah, thanks for the talk. I was just curious. I think you mentioned you used the default method. I don't remember the tool, and I was just wondering. It seems like that would be an important step, and there could be a lot of ways of doing that.
Yeah, so there are, I don't know how many thousands of embedding models you can find now on Hugging Face, but there's quite a few. We just used the default one with ChromaDB. I think John did a little bit of a research into other embedding models and found on a list of benchmarks, or there's like a leaderboard of embedding models. The one we used is actually like number 56 or something out of hundreds of models. We could have used the number 1 model. It would have been probably better, maybe a little slower to compute the vectors, but I think the embedding length that we have is, like I said, I think it's 384 dimensions. Some of the other embedding models go out to thousands of dimensions and are probably a little bit better. I think that's a great point that you bring up, though. And we didn't do any sort of exhaustive tests of what our results would have been or how long it would have taken to use a different embedding model, but there are a lot to choose from, and I think it would be worth us looking at least testing against maybe the number 1 embedding model, which I think actually comes out of Salesforce.com, makes that one now. Yeah, so yeah, that's a good point, and something that I think is worth looking at in more detail.
Thanks, Luke. Any other questions or comments? Yeah, I probably have a follow-on, Luke. So, so besides the work, I mean, here the data portal with a theme on tick species and the tick-borne disease. But are you able to see any potential of adapting this workflow, building the semantic computation, semantic embedding, and also the data discovery into any other domains like climate change, wildfire, or even like species, other topics?
Yeah, absolutely. I mean, this is in a lot of ways just an example. We did it with ticks and tick-borne illnesses because we're funded to do that under this project, but this could be applied to almost any disciplinary domain. You just have to, change the way change your prompts, but the workflow generally is the same. Not a lot of difference there. This could apply to almost anything. We have some use cases here internally at the University of Idaho we're interested in doing. So, for example, pointing it to our Vivo catalog, for example, to look at, to be able to ingest all of the publications from our faculty and students at the university, and then be able to power some sort of semantic search based on that. So we've got lots of other ideas for ways that we could apply this for sure.
Yeah. Second look. Maybe my last call to the audience. Do you have any questions or comments for Luke? Yeah, just a comment. I paste a link to the demo website in the chat box. It's data.tickbase.net. So anyone in the audience, if you have an interest, you can go there and take a trial of it. And then if you have any feedback or follow-up questions, you're more than welcome to contact either me or Dr. Luke Sheneman. I will be happy to follow your question, to forward your questions to Luke.
Great. Yeah.
Good.
Yeah, we look forward to feedback. Like I said, we've got some other things in the works, some other features that we're hoping to deploy. But if you have other ideas or you find something that doesn't work well, yeah, please let me know, and you can contact me through Marshall.
Okay. So thanks again, and Dr. Luke Sheneman, for the talk and your time attending our webinar.
Yeah, my pleasure.
Yeah. Next, we still have 20 minutes. So usually, we're a semantic web committee. So usually we use that time to discuss some committee business. So Dr. Sheneman and also anyone else in the audience, if you're not interested in the committee business logistics, you're free to drop off the meeting. The committee member